All right, today we're going to talk a little bit about simple ordinary least squares regression. Simple ordinary least squares regression. So I'm just going to start a note here. I'm talking about simple OLS regression. And this is a common procedure that you'll see in lots of different courses and with lots of different data, so we're just going to talk about it. What do we want to know? Well, when we're thinking about regression, we're usually thinking about two variables. Let's just call them x and y. And we're going to regress these against each other. And the usual information, the usual idea is that there's something in the x-axis that has information about what is in the y-axis. And that might be due to some mechanistic understanding. X might be causing y, or y might be causing x, or maybe they're not directly causing each other, but they're related in some way. And so let's go ahead and just start with some data that we're going to make up. We're going to use the rnorm function. And what I just typed here, if we put a question mark here with rnorm in the help, is we're going to be drawing random variates, random numbers from the normal distribution. So I used rnorm, where n is the number of observations we want. So I want 1,000 observations from a distribution that has a mean of 0 and a standard deviation of 1. So if I just run this, and now if I come down here and type, let's just plot x, you'll see that it's a whole bunch of numbers. Looks like the middle is 0, and they're sort of evenly spread. And I can also type a histogram of x, and you can see what a frequency plot looks like. It looks like it's centered at 0, has a standard deviation of 1. So if I type the mean of x down here, that's going to give me a number that's really close to 0, which means that the mean of this distribution is close to 0. That's what we asked for. And a standard deviation of x is very close to 1. So that's our 1,000 numbers drawn from a distribution that has a mean of 0 and a standard deviation of 1. Okay, let's talk about our y variable now. Well, right now, let's just pretend that y is exactly x. Y is exactly x. So when I run these two things together, that's my x, there's my y, and so now if I plot x and y, even though x is a random number that we chose, we specified that y is exactly equal to x. So all of the information in x is contained in y. And so we have a very, very good relationship here. And so let's go ahead and run a ordinary least squares regression. That's what we're going to call this here. And it's going to equal something called linear model, LM. Y is a function of x. So let's just take a moment to look at the function called LM. This is fitting a linear model. Our first element is called the formula, and in this case we say that y, or our response variable, is some function of x. That's what we want this model to estimate. We don't need to deal with any of these other elements. This is a very powerful function, but this is a very brief overview. So if we go back and we run our OLS, and now let's go ahead and type a summary of our OLS. We're going to see a couple things here. Let's go back to the plot. Here are our coefficients that we have to pay attention to. So our intercept is 1.053 times 10 to the minus 16. Very, very small number. And that's important because our intercept looks like it's almost exactly 0. And our slope is very nearly 1. And it should be 1 because for every element of x, there is an equal movement of y, because y is perfectly described by x, or x is perfectly described by y. And we can actually add a one-to-one line, or actually the line that is defined by these two numbers here. We'll just put AB line OLS and line weight equal 4, that will in fact throw on a weighted line on top of that. So that is the fit of those data. So it's a very, very good fit. A couple other things to look at here. So this is our estimate of our intercept and our estimate of our slope. Our standard error on those are very, very small. And what our t-value and p-value are, we're not going to get into that in this particular video. You can see we have a r-squared value of 1, which that means a perfect fit, and we have 998 degrees of freedom. That's because we estimated two things, an intercept and a slope, from 1,000 data points. So in this case, if we believe that they're independent values, we have 998 degrees of freedom. All right, so that is just a very, very simple fit of a line that we have pretty much made up. So let's now try a different scenario here, where we're going to say now x1 is now again normal distribution of 1,000 numbers, mean of 0, standard deviation of 1. y1 now is also going to be the same thing, 0 and 1. Okay, so let's take x1 and y1, let's run that. Now, y1 doesn't have any information about x, so when we actually plot x1 and y1, you'll see a very different story. It looks like there's one random variate plotted against another random variate, or it doesn't look like there's much of a relationship, or another way to say it is that the information held in x is not also in y. We can take, let's just copy this here. We'll just call this OLS1, and we'll do a linear model on y1 and x1, just like we had before. Let's go ahead and run a linear model. Let's take a look at the summary statistics of this. You'll see that our intercept is close to 0, our slope is close to 0, our r-squared is very low, which means there's no information in there, and we can throw our AB line on there. Looks like a pretty terrible fit, and it should be a terrible fit because there is in fact no information in y1 that is also in x1. Now, one way to check to see whether or not one of the main assumptions of the ordinary least squares regression is to look at something that's called the residual. The residual. Now, what is the residual? The residual is the difference between this point and the fitted point, or the difference between this point and what the model predicts. And ordinary least squares regression, one of the assumptions is that the residuals are normal. Residuals should be normal. So, or the residuals should follow a normal random distribution. We can extract the residuals if we just do a residuals of OLS1. That's what they are. And then we can go ahead and plot them, do a histogram of this, and you will see that, yes, the residuals are a normal distribution. So we have x1, y1. We have a terrible model between the two, but at least the residuals are obeying the ordinary least squares regression. Now, we didn't do the residuals up here when x is exactly y, because in fact there are no residuals, because it was an exactly perfect fit, so we didn't do this exercise up there. Another way to look at this is by looking at a function that's called QQ-norm. QQ-norm. So if we do a question mark QQ-norm, these are what's called quantile plots. So what we can do is look at the quantiles of the data and figure out whether or not the data or the residuals are following a normal distribution. So let me just give you an example of this. So if we type QQ norm, and again, you can read more about this. This is just a very quick overview. Let's do a QQ norm of the residuals of this OLS1. Run that. You should get something that approximates a straight line. And we're going to do QQ line. I'm going to do the same thing. I'm just going to copy and paste this. And make the color of the line red. So, and the idea here is that if it really is a normally distributed residual, when I look at the quantiles against the theoretical the actual quantiles versus the theoretical quantiles, they should pretty much be on a one-to-one line, which looks like they are. They're pretty close to that. Okay, so far we did a perfect fit here. We did a exactly imperfect fit, both with ordinary least squares regression. And so now we're going to mix it up a little bit. So let's go ahead. I'm just going to copy this. I'm still going to keep x1 as our norm 0, 2, 1. And now I'm going to put this, I'm going to make this x2. So don't get confused here, make a new object. y2 is now going to be x2 plus some error. And this really is what we are thinking about when we're thinking about an ordinary least squares regression. You'll notice that this is a mixture now of our first case where y was exactly x, and our second case where y was just another random variable with respect to x. Y in this case has x in it, and we're also adding some normal error, some normal distribution. And so this is what we would call our deterministic on this portion here, this x2, versus our probabilistic, or this is our function and our error. So when we run these two things, x2, y2, we're going to get something a little bit different. Again, I'm just going to borrow some code from up here. I'll just grab this here. In this case, we'll just make this OLS2. y2 is a function of x1, and we'll do a summary of this thing. And let's see, we will also have to plot x2 and y2. Okay, so let's do this. Okay, what do we have here? So here we've got, here's x2, and here's y2. So x2 is our random numbers. y2 now has information of x2 in it, but we're adding to that some random variation, and that's what we see here. So you can still see that there is a relationship, but a fair amount of scatter around that. So here's the relationship, and here's the scatter that's added on top of that, and that's what we're getting in this plot. We can run the ordinary least squares regression, and we can estimate now what the x-intercept is. It's very close to 0. And the slope, which is very close to 1, which it should be because we have x2 in there. So it's almost a 1-to-1 slope. Our r squared is something like 0.47. And we're going to add a best fit line to this. Oops. Sorry about that. This should be OLS2. Just run this again from plot. There we go. That is now the line that is the best fit of that data. And just like again, we can check our residuals. So let's check our residuals. Histogram of our residuals for OLS2. They look pretty normal. Here's our quantile plots for our residuals. Again, looks like they're right on that line. Okay, so far so good. All right, what else can we do here? Well, let's do something a little bit different. We can reformulate this. Let's do x3. No, I'm just going to copy this. x3 we're going to keep the same. y2 is now going to be y3. We're going to take this out. Now, I'm going to do it this way. All right, what did we do here? So x3 is a bunch of random numbers. y3 is now going to be random numbers that have, instead of a mean of 0, they have the mean of x3 and the standard deviation of 1. So the mean of x3 is 0, the whole thing. But what this does is it looks at each point in x3. So if we look at x3, I'm sorry, let's go ahead and run x3 first. There's 1,000 numbers in here. So our first point that we pull from y3 is going to, that first variate is going to have a mean of 1.56. The second one is going to have a mean of 3.3. So when we run y3 like this, it's going to look really similar to what we had before. So I'm just going to copy this here. I'm going to make this y3 or x3, x3. Go ahead and plot this. Looks, it looks really similar to what we had in just a little bit ago. Change this all to 3s. So we can run this. We get our best fit line. Here's our estimate of our slope, really close to 1, which it should be. And here is our histogram of our residuals. Again, that's just confirming that our residual error is normal, which is one of the assumptions of this method, and then our quantile plots look pretty close to being 0. Okay, so let's break something now. All right, so let's go ahead and do x4 is again 1,000 random numbers, and y3 is not going to be a random normal distribution. Let's go back to this formulation. Right, so this is what we had up here in this case. Instead of drawing from a random distribution, we're going to draw it from something called RL norm. So RL norm is the log normal distribution. The log normal distribution. So let's just play with this a second. So let's do a histogram of RL norm with a 1,000 variates, mean of 0, standard deviation of 1, and you're going to see that we've got our definitely not a normal distribution. There's a whole bunch of small numbers and a few really big numbers out here. And so when we do this on this, on x4 and y4, and then we plot x4, y4, you'll see the difference. Okay, it looks like we got a whole bunch. Here's our line again, but notice all the scatter is up here. Really big variance off of this thing. And let's go ahead and look at the linear model. We still have a slope close to 1. The intercept is not quite 0, definitely not 0. But take a look what happens when we add the line on top of it, the best fit line. And you're going to notice right away that something's up, because it looks like, you know, this model assumes that the error is sort of normally distributed around the fit, but you can see that that's not the case. And this, you have a lot more points down here that are concentrated compared to some points that are really tugging that line up here for the best fit. So we already realize that something is amiss. So if we run our now residuals, we do a histogram of the residuals, right? Not a normal distribution at all, right? Very much lopsided to one side, and we do our QQ norm plots, and you can see all the points should be on this line, but they're not. They're strongly deviating from it. And so this is a hint that perhaps the assumptions of the OLS model, which is to have normally distributed residuals, or another way to say that is that you have some deterministic function with some random error around it that's normally distributed, is not the case. And you can kind of see that here already, that we're a little suspicious. If we look at this fit, we go, okay, I guess that's through the middle of the points, kind of, but the points are not evenly distributed on either side of this line, which is one of the assumptions to get good OLS estimates. So if we scroll back in our plots a little bit, you can see that here, where we've got a fit down the middle, and it looks like there's the same sort of distribution of points on either side of this line, that we would know that that data is appropriate for ordinary least squares regression. That's not what we have here. We would have to do something slightly different, but we're not going to talk about that. Instead, what we're going to do is we're going to go ahead and read in some data that we have from this class. So we're going to go set our working directory to, this just happens to be where my data is. Yours might be different. Let's see, nest, sports 6. 19. So I'm going to set my working directory there. Yours may be different. You can also come up here and go to Tools. No, it's not there. It is in where is it? Session. There it is. Set working directory. You can choose the directory where your data is. Right, for now though, I'm going to make a thing called D, which is going to stand for data, and I'm going to read read a CSV file in, which is the H price. So this is home price 2 versus NOx gases, and I'm going to do header equals true. Let's go ahead and run this. And if I take a look at, I have the price of a house, what the NOx gases are, and we're not going to do anything with rooms or ST ratio at the moment. What we're going to do right now is just simply plot D, assign NOx as our X value. So that's pulling out this column right here. That's the name. That's name NOx versus D $ price. And let's do a point character equals 20. That's going to give us a nice solid point. xlab equals nitrogen oxide concentration parts per 100 million. And our ylab is going to be median housing price in dollars. All right, so there's our data of median housing price in dollars, and this is our nitrogen oxygen. It looks like we have some kind of negative relationship here. And so what we're going to do is we're going to run a function, an OLS of NOx, our linear model. It's going to be our response here is price. Price is some function of the NOx. We'll do that. And now we will go ahead and add the AB line of OLS NOx finally equals 4. That's going to thicken the line up for us. Should put the line on there. So that's the best fit. And now let's take a summary of OLS NOx. Summary shows what our intercept is. Our y-intercept would be 4,100,307.8. That's where that would be 0. Where NIT ox would be 0. That would be the housing price. And then for every unit of NOx, it goes down by $3,386. That's how to read this. So as our nitrous oxide concentration increases, we go down by about 3,386. You can kind of see this here. So here's nitrous oxide here at 5, and here it is at 6. And the difference between where the line is here and where the line is here is going to be $3,386. So for every unit that we're going up here, we're going to lose $3,000. So that's the way to think about this. So let's go ahead and just take a look at the histogram of the residuals of OLS NOx. Let's see whether or not this is behaving. Looks kind of normal. There's some things that are a little off out here. Possibly could be a little bit of a problem here. Or let's take a look now at our QQ norm. Okay, not quite a straight line. And let's put this in here. Okay, pretty far off normal. I mean, this part in the middle here seems to obey, but the tails aren't behaving so well, so it could be that, when you look at the fit, yeah, there's a lot more points up here than down here. Possibly there's some other effect that we need to put into the model. So ordinary least squares regression maybe isn't totally bad for this fit, but there may be other things to think about just besides nitrogen oxide in terms of median housing price. So that's just a really quick overview of ordinary least squares and how to think about it a little bit. There's lots of help pages. Okay,